Great. All right. Hello, everyone, and welcome to our very first meetup of Tbilisi Data Science, which, just to give you a little, maybe one or two words about what it is, it's an online, at the moment, online organization for meetups around data and the current relevant topics, basically. And we will try to have some discussions about some of the trends that we are seeing currently in data, and also looking at some of the experiences from the industry and academia. And our very first guest speaker is going to be Frank. Frank is an educator in data science and AI topics, and also an ex-Amazon where he was a senior manager there and had to work with data science and AI products in the early days, hence the title of today's meeting. So hello, Frank. How's it going?
Doing good. Thanks for having me tonight.
Great. So yeah, I think we can jump straight to the topic, which is about the early day Amazon AI products and data science products. So could you please give us more information about it?
Yeah, I'll just kick off my slides here. And by the way, if you all have any questions as we go, feel free to barge in and interrupt me. You can use that React button at the bottom and raise your hand, and I'll try to keep an eye out for that. Or if you just want to slap your questions in the chat, we can address them later. So however you want to do it, it's fine by me. But yeah, let's kick off the slides here.
Great.
And yeah, like you said, I was there. I was in the room when it happened, folks. So this is going back in time to the year 2003 when I started at Amazon.com. So Amazon was a much smaller place back then. Let me just confirm that you can see my slides there real quick.
Yes.
Cool, we're good. All right, yeah, so we're going to talk about kind of like the formative years of data science and AI at Amazon. We didn't even call it AI and machine learning back then. It's just,
Yeah.
stuff we did. So, back then this stuff didn't really have a name, but we did sort of pioneer a lot of not just data science and machine learning algorithms back then and
Hmm.
recommender systems, but we also pioneered a lot of the systems for delivering these results at scale at a massive website. So, going to give you a little bit of a trip down memory lane as to how we did it back then and how that
Hmm.
evolved over time to how we do it today. So,
Great.
cool. Yep. And here's a picture of Jeff Bezos back when he had a little bit more hair and was not buff. Very different man back then, I assure you.
Hmm.
So yeah, going back in time, this is actually the Pacific Medical Center building in Seattle on top
Hmm.
of Beacon Hill, and believe it or not, almost all of Amazon fit into that building back then. This was
Wow.
actually a an old hospital that they kind of decommissioned a long time ago from the 1920s, and that
Hmm.
was the Amazon office for quite a long time. My office was on the fifth floor somewhere there, facing out there. So fun times. Jeff's office was like in that big area where all the windows are, and that big
Hmm.
open
Yeah.
area up top there. Interesting times for sure. But yeah, I mean, it was a much smaller company back then. So, you know, Amazon was just starting to branch into music and DVDs and out of books. So it was a very early time
Hmm.
for Amazon. It was an exciting time to be there and be involved in its explosive growth after that point. I joined in the personalization team, and we call that P13N for short. And that's what we called it back then. We didn't call it machine learning. We didn't call it AI. We called it personalization. Our
Hmm.
method, our entire meaning in life was to try to recommend items to people that they didn't know that they wanted until we showed it to them, right? So
Yeah.
the most popular feature that we created was people who bought also bought. And you probably remember this from Amazon
Hmm.
back in the day. So you got to look at a book or anything else, and it says, okay, people who bought this book also bought this other stuff. And the idea
Hmm.
is to upsell you there to make you buy additional stuff that you might not have thought of before. And it turned out to be pretty effective. So this is what we call internally similarities, things that are
Hmm.
similar to other things. And the thing is that similarities tend to surface complementary items for upselling things. So if you look at what people also bought with something else, that's going to be an upsell opportunity, that kind of a data, right? So it's other stuff you might like. We also did the same trick using clickstream data, what people were viewing, and that would be people who
Hmm.
viewed also viewed. And that would give you effectively substitute items, so more of a cross-sell opportunity there too. And as you can imagine, upsell is more valuable than cross-sell. So, if we had good data for people who bought as overviewed, then that would be preferable. However, it depends on the product line, right? So if you're
Hmm.
having someone who's shopping for electronics, for example, They might want assistance in finding just the right receiver or just the right turntable, whatever it might be, just the right television. In that case, substitutes might be the right thing to show to those people. And I'll get into how
Hmm.
this all works shortly. Well, right now, actually. So, under the hood, it's just straight up cosine similarity. There's nothing fancy going on here. And I'm going to dive into the details of this algorithm, but it's surprisingly simple. The only thing that's a
Hmm.
little bit different, though, from our approach is that we started with this item-based approach. So when you read up on recommender systems, in the literature or online or whatever it is, usually they take a user-focused approach. So they'll say, okay,
Yeah.
what
Hmm.
people are similar to me, and what did they buy that I didn't buy, right? So that's one way of
Hmm.
going about it.
Sure.
Look for similar users, look for stuff that they like that you didn't know about, and recommend that stuff. That's fine, but there are reasons why you would probably want to do that a different way and just use that based on items instead. So, one key insight there that would drive that is that relationships between things tend to be more stable than relationships between people. People
Okay.
change over time, their interests change, their point in life changes, and what they want is not going to be a constant thing. However,
Hmm.
a math book is always going to be a math book, right? So,
Sure.
those similarities between items tend to be much more stable over time and long lived. Also, there's the advantage that there tend to be fewer things in the world than people who want to buy them, especially at a
Hmm.
place like Amazon. So there are some efficiencies involved in making everything item both focused instead of user focused. It just shrinks down the computational complexity that you need to deal with.
Hmm.
So, and by the way, this ended up driving about 20% of Amazon's revenue at the time.
Oh,
So
wow.
believe it or not, similarities, just people who bought also bought and people who viewed also viewed, that was 20% of Amazon's business back then. And even back then, it was a $1 billion company. So you do the math. It really earned its keep for sure.
Yeah, that's truly a big number. And was there any like maybe an experiment steps that you had to take in order to take this approach, or how did you find? Did you have any prior knowledge to what this could result in, as to talking about the revenue being 20%? Did you have maybe
Yeah.
any
So, like, how do we
predictions on it?
No, it was a fortunate accident, as I recall.
Hmm.
So they had already, come up with the algorithms before I joined in 2003. They actually started
Hmm.
working on this around 2001.
I see.
And the story, as it was told to me, is basically they hired a couple of guys from the University of Michigan who were doing a
Hmm.
lot of research on recommender systems. And I still use their data set to this day in my courses. It's the Movie Lens, Group Lens
Yeah.
data
Hmm.
set. So they were focused on making movie recommendations and kind of experimenting with different ways of doing that algorithmically. So basically, Jeff hired a couple of those guys, John Rouser and John, oh gosh, I'm forgetting his name now. But they were the real pioneers there. They worked with my boss at the time, Brent Smith, to operationalize that and actually apply that to Amazon's data. So as far as I know, they
Hmm.
didn't really experiment with other techniques. They were just, starting from where that academic research was leading them before they came to Amazon.
Hmm.
So that, they weren't doing like any frequent pattern mining or
Yeah.
you know hidden Markov models or anything like that. They started with this collaborative filtering approach from the get-go, and
I
it
see.
worked out. Yeah. So, um, but yeah, as for how let's talk a little bit about experimentation though, since you asked. So
Hmm.
there are many ways of doing this, right? So cosine similarity is just one way of measuring the similarity between things or between people, and
Yeah.
that is what we ended up using for the most part. In truth, we ended up doing something even simpler than that, but I'm not allowed to
Hmm.
tell you the details. Also, I don't really remember all of them at this point.
Hmm.
But the good thing about cosine similarity metrics is that they're super easy to compute. So this scales really, really well. There are no big
Hmm.
artificial neural networks involved or large language models.
Sure.
It's just this formula here, which is super simple, right? So let me
Hmm.
break this down for you. Let's say that we're looking for the similarity between two things called X and Y. Maybe it's a math
Hmm.
book and another math book. I don't know. Or it could be two people. Doesn't matter.
Yeah.
Either way, there's going to be like a very large vector associated with that thing or that person, but that represents
Hmm.
for a thing all the people that bought that thing, or for a person, all the stuff that person liked, right? So you have this
Yeah.
vector across all the items in the entire catalog. And what items did a single person buy? So that's what we're looking at when we say X sub I or Y sub I. It's going along that whole vector of
I
the
see.
entire space of items or the entire space of people, depending on how you approach it. And all you got to do algorithmically is add up all the products of those two things for a pair of people or a pair of items that you're interested in to compute the similarity for. And
Hmm.
at the same time, while you're adding that up, you just add up the squares of those values, sum those up at the end. Then there's just two
Hmm.
square roots at the end of the computation, super quick, and you're done. You have a cosine metric. So If you remember your trigonometry, this is kind of
Mm.
what it breaks down to at the end of the day. And it is just
I see.
trig, which is kind of cool. So, by thinking of people as vectors in this higher vector space of stuff they bought, or items as this higher vector space of people
Mm-hmm.
that bought that item, you can just break this down into simple trigonometry, basically. And that's basically the
I
underlying
see.
trick there.
Mm-hmm.
So, pretty cool. It's hard to visualize when you're talking about multiple dimension space, but the
Mm-hmm.
math itself is pretty straightforward. And you can imagine how quickly this translates into an actual bit of computer
Mm-hmm.
code. Now, the main issue, though, is that these vectors are very sparse, right? So if an
Mm-hmm.
individual
Sure.
person has not watched every movie in the world.
Mm-hmm.
Um, I know one guy who did, my old boss at IMDb, but he's definitely an outlier. So the problem that
Okay.
we have here is, if we're looking at Bob, Ted, and Alice and trying to figure out how similar these people are to each other, um, it's going to be tough to get that information, right? Maybe
Mm-hmm.
Bob watched Indiana Jones and Alice watched The Incredibles, but maybe Ted didn't watch any of these movies, so I can't say anything about
Mm-hmm.
Ted.
Yeah.
And that's why it really depends on the scale of the data that you're dealing with. So,
Mm-hmm.
Amazon being Amazon and being really big, our advantage is that we had a ton of data. We had lots and
Mm-hmm.
lots of items. We had lots and lots of users. And when you have data at that scale, sparsity doesn't really matter so much. It
Mm-hmm.
does matter from a computational standpoint because you don't
Sure.
want to
Mm-hmm.
waste all this space storing empty data, right? So you have to
Mm-hmm.
come up with these sparse arrays and stuff to try to manage that. Um, but the fundamental problem is sparsity. So if you
Mm-hmm.
take these techniques and try to apply them to a small data set, you're going to get lousy results, right? So
Sure.
in my courses, I include a 100,000 rating data set from Group Lens, and the results are kind
Mm-hmm.
of iffy, because even with 100,000 ratings, the sparsity problem is still an issue. So we
I
kind of
see.
cheated a little bit by having that much data.
Okay.
Uh, by the way, let me know if anyone has a hand up or anything. For some reason, I can't see it in my UI. So just
Yeah, sure.
barge in.
At the moment, no raised hands, but yeah, I'll let you know.
Go. Cool. All right. So you can also see that this is kind of like a 2D matrix, and you can
Mm-hmm.
treat this whole thing as a matrix multiplication problem at the end of the day. And guess what? Neural networks are good at that too. So that's kind
Yeah.
of foreshadowing as to where this ends up.
Mm-hmm.
Now, there are other ways of doing cosine similarity. So one is what we call the adjusted cosine metric. And the difference here is instead of just looking at the raw rating values, so if you have a user who rated movies 1 to 5 stars, we're not going to take their raw 1 to 5 number there in this algorithm.
Mm-hmm.
Instead, we're going to take the difference between that rating and the mean for that user's rating of everything else.
I
And the
see.
idea here is to try to deal with trolls, right? So if you have somebody who just rates everything 1 star because they hate everything, you don't want them polluting your data. So someone
Yeah, of
like
course.
that, if they actually rated everything 1 star, they would not count for anything because the difference
Mm-hmm.
between their ratings and the mean would always be zero. So
Mm-hmm.
kind of a cute trick there. In practice, though, it doesn't really help. In fact, it hurts more than it helps because a lot of people only rate one thing. And in that case,
Mm-hmm.
that one rating is going to be the same as their mean, and they just get thrown out the
Exactly. Yeah.
window and you lose all that data. So
Mm-hmm.
um, so it sounds like a good idea, but in practice, it just makes things worse. But there is another twist on that called Pearson similarity, very similar idea. The difference here is that instead of looking at the individual means, we're looking at the overall means. So,
Uh-huh. I see.
if somebody rates Star Wars 1 star and everyone else rated it 5 stars, that's going to have a lot more weight because that person has a
Mm-hmm.
very strong opinion and an unusual opinion about Star Wars. And maybe we
Mm-hmm.
should weight that information more heavily, right? So,
Yeah, makes sense.
um, yeah, I mean, eh, it helps a little bit, in some data sets, but we did actually try this at Amazon and it didn't do any good. In fact, it made things a little
Uh-huh.
bit worse.
Okay.
So, what we found time and time again is that the simpler the algorithm was, the better it worked in the real world.
Mm-hmm.
And the more you try to embellish on it and make it complicated to deal with problems that you imagined happened, the worse you ended
Yeah.
up making things. Um, but we did try this one, didn't work. But it's a good one to know about for sure.
Mm-hmm. Okay.
But again, the secret sauce was just the scale of the data we were working with. So
Mm-hmm.
it really makes a lot of problems go away when you have massive data. So, if you're going to be a data scientist or a AI engineer, my advice is to work at a company with a lot of data. For one thing, there's something called the cold start problem. So what do you do when you
Mm-hmm.
have a brand new item or a brand new user that you don't have any behavior data for yet? You're kind of
Okay.
stuck in that point in a smaller data set. You might
Mm-hmm.
have to fall back on recommending things based on the attributes of that item itself, its physical attributes or the
Mm-hmm.
genre of the movie or things like that. But at a place like Amazon, it just doesn't matter because, in a few seconds, somebody's going to buy that thing and you'll have some
Mm-hmm.
data. So we just didn't care.
Yeah.
Um, but again, this is actually an interesting statement here. Like while I was at Amazon, it was always the case that more data would trump more clever algorithms. And
Mm-hmm.
this is advice that's been repeated, in the data science world quite a bit since then. However, that argument's kind of falling apart these days, right? So,
Mm-hmm.
in the field of large language models, we're kind of running out of data, right?
Mm-hmm.
And we're seeing that, there is no second internet to train these systems on. So
Mm-hmm.
people are kind of inventing this, fabricated data sets and kind of
Mm-hmm.
like scraping the bottom of the barrel for more data, but it's not really producing noticeable improvements in the models at this point.
Yeah.
So these days, I'm not sure that advice holds anymore. We might be at the point where what we really need are more clever algorithms because we don't have any more data. So more data is not going
Yeah.
to help. We're kind of at that point of diminishing returns. But assuming that you're not working with the entire internet as your data set, I think it still holds true that more data and better data is probably going to be more important than having really clever
Mm-hmm.
algorithms, right? Now, the other issue that we had was kind of managing the scale of all of this operation. So the similarity service that vended that people who bought also bought data got thousands of hits per second, even back then. And
Mm-hmm.
today, I don't even want to think about what that would be. And back in 2003, we didn't have Docker, we didn't have Kubernetes, we didn't have AWS. Fun fact, even when AWS was released, it took a few years for Amazon to start using it internally because we didn't trust it.
Oh,
So
okay.
most people don't realize that because they kind of told people the opposite. But yeah, we still had to deal with massive scale somehow. So how did we do it? So the key was just being super efficient in our code and trying to be super simple in what we were doing.
Mm-hmm.
So efficiency and simplicity won the day, right? So the more efficient your servers were, the fewer servers you would need to have. And the fewer servers you
Sure.
have,
Mm-hmm.
the less likely a server is to go down on you at 2 in the morning. And that's why there's a
Mm-hmm.
picture of a pager here, because back then, that's how operations worked. If your server suddenly became a little bit too slow at 2 in the morning, whoever had
Mm-hmm.
pager duty that week would get woken up by their pager and had to get out a very
I see.
clunky hardware VPN device to try to log in and figure out what was going on. You didn't want that to happen. So we were highly motivated to make our
Mm-hmm.
systems simple and efficient because, the simpler it is, the fewer things that can break. How did it work exactly? I mean, yeah, we kept it simple. So back then we didn't have, NoSQL data stores or anything like that.
Mm-hmm.
Instead, we just had what was called a Berkeley database, Berkeley DB, which is a very early key value store.
Yeah. Mm-hmm.
What we would call a NoSQL database today, even though NoSQL
Mm-hmm.
databases mostly use SQL now, but that's another story. Um, and they all just had a copy of the same exact data. Their only job was to read that database and spit it back out to the front end web server. And the
Mm-hmm.
traffic was just distributed by this big old hardware load balancer. And, more often than not, the problem was that load balancer failed on us, and then we had
Mm-hmm.
to go wake up networking instead. So, but again, it was simple. That's the
I
key.
see.
Now, it's not that you can live without systems that deal with containers and dealing with distributing those containers to servers. We just
Mm-hmm.
had to build our own because there wasn't another one out there at the time. It was called Apollo internally, and that handled the problem of getting bits on boxes and restarting
Mm-hmm.
the servers when new software or new data was deployed. So, we kind of like rolled our own systems there before they were really available to the general public, and
Mm-hmm.
it worked pretty well.
That's actually a very interesting topic. I think, I mean, the fact that you didn't have any containerization back then and you had to actually go through some of the hard steps to actually maybe find some more clever solutions. Do you think that's maybe in today's like cloud native environments, like there might be some aspects of the early scaling strategies that still holds up today in cloud native environments?
Absolutely. I mean, I still preach simplicity to everybody that will listen.
Mm-hmm.
So, it's still true that if you have a very efficient system, you will need fewer servers. And,
Mm-hmm.
even in the cloud, more servers is more problems.
I see.
And more complicated systems is going to be more ways for things to break. So,
Mm-hmm.
if you can break things down to simpler implementations, I think that's still solid advice today.
Mm-hmm.
And
I see.
I think a lot of people are guilty of overcomplicating things just to show how smart they are. So, like, I know all these web services. I'm going to tie them all
Mm-hmm.
together and configure them in a fancy way just to show how awesome I
Yep.
am and get a promotion to principal engineer. But in reality, that's going to make your life difficult. So,
Mm-hmm.
simpler and more efficient is better for sure.
Mm-hmm.
Especially when I see people like deploying Python code into production. I mean,
Mm-hmm.
if that's wrapping something more efficient, then that's cool. But, at
Mm-hmm.
scale, it's probably not the best choice.
Yeah, true.
But yeah, PagerDuty sucked. I wanted to throw mine into
Mm-hmm.
Puget Sound at the time for sure. Um, That was interesting too, because the people that developed the systems were also on the hook for supporting those systems, which, created a very good
Uh-huh.
incentive for making them solid.
Hmm.
The other side is how do we crunch all that data? So even back then, we had a
Hmm.
lot of purchase data, a lot of view data that we had to compute those similarities on. And these days you might use something like Apache Spark to like do that at scale and split it out into a
Hmm.
bunch of different servers. We avoided all that complexity too because we just had really, really tight code. Back then, for prototyping, Perl was kind of the Python of the day. So Perl was the
Hmm.
scripting language of choice for kind of like messing around and playing with stuff. But when we actually moved this into production, we wrote some very highly optimized C code. It wasn't even C++, actually. The slide is wrong. It was just straight up
Uh-huh.
C.
Yeah.
Because we wanted that to be as fast as possible because we didn't want to ever have to need more than one server to do it. That would like
Hmm.
introduce all this complexity and all this distributed system overhead. We just didn't want to go there. We wanted this thing to run reliably
Yeah,
all the
sure.
time. I mean, of course, we would have a backup server ready to go if that one server
Hmm.
went down at all times.
Hmm.
But again, simpler is better. If you can do this on one machine and do it reliably, you win. Um, and believe it or not, we ran this on a single server for the entire time that I was there, for the entire catalog of Amazon. And if you think about it, it's not a lot of data you have to
Okay.
deal with. These Spark vectors don't take a whole lot of space.
Yeah. Hmm.
Even if you have millions of customers, that doesn't really add up to a whole lot of space
Hmm.
that you have to deal with, and you can just deal with it over
Sure.
time.
Hmm.
It's not as scary as it sounds. The thing that did break a lot was actually the data warehouse. So, where did this data
Okay.
come from? Back then, we had a central data warehouse that the entire company shared. And every night we depended on an export of all the, new orders from the day before and all the new
Hmm.
views of the day before to compute these things. That's what actually ended up breaking it the most.
Uh-huh.
Um,
Okay.
Back then we had this very big, expensive Oracle database, and they had replication systems, but they didn't really have a way of distributing it back then.
Hmm.
And we had to hire these very expensive, specialized database administrators to make sure it all kept
Hmm.
running. And everybody was always fighting over their time and their attention because things
Yeah.
kept breaking. So that was the main problem in practice, just getting the data. And of course, that's still a problem today.
Yeah, and do you think that the same reason holds here, that some overcomplications happen in big systems?
Yeah, I don't know. I mean, I think a lot of the changes in the database world are for the better. Having a
Hmm.
giant monolithic Oracle server is not a good idea because it will just fail in horrible, horrible ways.
I see.
So, the data lakes that we have today, even though they're maybe a little bit more complicated and involve more servers, I
Hmm.
would rather work with one of those over a giant Oracle host
Yeah,
any day, you know.
sure.
So. Yeah, so the other part of personalization was personalized recommendations. So, one thing is people who bought also bought, but we can also recommend stuff, individual items that we think you as an
Hmm.
individual might be interested in. And the way we did that was something called item-based collaborative filtering. And the
Hmm.
idea here is basically recommend things that are similar to the things you like. So again, the insight here is to focus on things and not people. And by liked, I
Okay.
mean you rated it or maybe you purchased it. I mean, purchasing something is like the ultimate rating. You opened your wallet and you gave money for this thing. So
Hmm.
there is no better data for someone being interested in an item than they actually bought the thing. People can't game that
Hmm.
either, which is actually really useful as well. And there's a little bit more of an art to this, so you don't want to be recommending things that are just painfully obvious. So if I'm reading
Hmm.
a book in a series, recommending the next book in the series is probably a really safe bet, but it's not really going to generate any incremental sales because they would have bought it
Hmm.
anyway, right? So
Sure.
what you really want to achieve is showing people things that they love, but they didn't know they loved until they saw it. We call
Hmm.
that serendipitous discovery. And that's a hard thing to measure, right? So there was a bit of an art to this where we would just sort of apply some human judgment as to how diverse should these recommendations be across categories, how
Hmm.
novel should they be in terms of whether or not you might be familiar with them or not. So lots of fun experimentation going on in that space.
Hmm.
And actually, way back then, Jeff Bezos's dream that he kept challenging us with was to make recommendations so good that we could just take over the entire Amazon homepage with a picture of one item and say, "This is the one thing that we think you're going to love. Go buy it."
Oh, wow.
um, we never quite got to that point because, well, the sponsored placement people kind of won at the end. But that was the
Yeah,
original
that's a
vision.
challenge.
Yeah, he was good at making challenges. But yeah, so on this item-based approach, we're going to flip that matrix around, right? So the idea
Hmm.
here is that instead of focusing on people, we're focusing on things again. So in this
Hmm.
case, we're going to if we're going to be recommending movies to people, we might take a look at the users that rated each individual movie. as opposed to the movies that were rated by each individual user, right? So we kind of flip this around. So in this
Mm-hmm.
example,
Okay.
Bob watched Indiana Jones and Star Wars and liked it and loved Star Wars, Empire Strike Backs and Incredibles.
Mm-hmm.
So you can kind of see where the math is going here. There's going to be a link between Indiana Jones and the Incredibles, for example. And I won't like dive into the math here, but if you just apply cosine similarity and
Mm-hmm.
plot the cosine similarity scores between each individual movie that we looked at there, it looks like this. And because our
Mm-hmm.
data was so sparse, they're all going to be one or zero. But in the real world, where we have more information, you'll get more interesting numbers here that you can use to sort things
I
by.
see.
But it's kind of interesting that even with that very sparse rating information we had, we do have a lot more information about pairs of movies than we had before. So things
Mm-hmm.
really do work out better with that item-based approach.
Mm-hmm.
So just to drive it home, let's say Bob here liked Star Wars. With this new approach, we can then say that Bob might also like Indiana Jones, The Incredibles, and The
Mm-hmm.
Empire Strikes Back. And that's all we're really doing under the hood with recommendations. We look at items that are similar to stuff that Bob liked. We filter
Mm-hmm.
out stuff he already liked and kind of sort them by how strongly we think that might be a good recommendation.
Mm-hmm. Great.
Now, the other problem here is how do you measure the success of these systems? And I think this does have a lot of analogs in today's problems as well.
Mm-hmm.
So what people tended to do, and still do in the academic literature, is they'll break stuff into train and test, data sets, which
Mm-hmm.
is a reasonable thing to do. And they will take their algorithm, their model, and they'll say, how well does this model predict what these people would have bought, if I don't know if they
Mm-hmm.
bought it or not. And I mean, if you don't have a better way of evaluating something offline, then maybe that's a good place to start. The problem,
Yep.
though, is that metrics like that, like a root mean squared error and like how good you can predict stuff that people already bought,
Mm-hmm.
it's just going to measure your ability to recommend things that people were going to buy anyway, right? And again, that's not
Okay.
what you want to do. You want to recommend stuff they didn't know about, and it's not going to be
Mm-hmm.
possible to measure given historical data, unfortunately. So
Mm-hmm.
we didn't do that at all. Instead, we just ran, fancy A/B tests all the time, basically. All we cared about is did people buy more stuff because of our algorithm or not,
Mm-hmm.
right? And that's all that we focused on. So a huge, huge thing within Amazon back then, and even today, I assume, was what they called web labs, which is kind of their fancy
Mm-hmm.
A/B test platform. And this got a ton of attention because it was so important to the company. Back then, I was working with Ronnie Kohavi was my boss for a while. He's
Yeah.
kind of a big name in the field of online testing. But yeah, all we cared about was the p-value on those
Mm-hmm.
experiments. Did we actually move the needle on purchases or not? And even that's more sophisticated than a lot of people do with A/B tests today. It drives me bonkers when people like test a new title on a web page and they get like 10 people that look at it and they draw conclusions based on those 10 people.
Mm-hmm.
Like, it's just chance, people. My gosh, be a little bit more careful
Yep.
about it. Because I mean, even at Amazon, in our scale, it was really, really hard to win a web lab.
Mm-hmm.
A small change on a website is going to be very hard to tease out an effective on actual purchases. And it
Mm-hmm.
normally would take months to actually get a result on even a major change in a web lab, even with Amazon's scale of data. So
Yep. Mm-hmm.
measuring this stuff is harder than you might think. Another thing we learned is that user interface changes would
Mm-hmm.
typically have a much larger impact on the web lab results than algorithmic changes, right?
Mm-hmm.
So don't assume that your algorithm is all that matters. How you present the results of that algorithm
Yep.
matters
Mm-hmm.
more, and
I
that's something
see.
that we learned
Mm-hmm.
over and over and over again. Just how you
And
present it.
like, so you basically mentioned that, like, whenever you wanted to see the effectiveness of the algorithm, you would go through the A/B tests. But before you started the A/B test, I mean, before the algorithm was actually shipped, how did you evaluate what would be the one that you would ship?
Um, So toward the end of my reign there, people were using RMSE as a sort of an
Mm-hmm.
initial measure. But before that, it was just qualitative. We would
Uh-huh.
cherry pick a few items that we knew were problematic and see if they felt better to us or not.
Uh-huh. I
And it
see.
was really that simple.
Mm-hmm.
There was no barrier to entry for running these web labs at the time. So if you had an idea and you wanted to try it, you would just try it. We didn't care if it had a negative impact, as long as, if it
Ah,
was a
okay.
really
I
bad
see.
negative impact, we would pull
Mm-hmm.
the web lab pretty quickly, obviously.
Mm-hmm.
Um,
Yeah.
but it was very much a culture of experimentation and just trying
Mm-hmm.
new stuff and throwing spaghetti at the wall and seeing what sticks.
Mm-hmm. I see.
Yeah. So, in terms of data science at Amazon, again, this is really the most important application of it within the
Mm-hmm.
organization. Just the ability to run a lot of experiments concurrently
Hmm.
and measure their results. And that turns out to be really hard because you want to make sure that these different
Yep.
experiments that are running don't interfere with each other, which is super tricky.
Uh-huh. Okay.
Let's talk about that a little bit.
Hmm.
So, even if you get a good web lab result, it still isn't a guarantee that you're doing the right thing, unfortunately. So, even
Hmm.
if you have a low p-value score and you have a really good experiment designed, there's still a chance that it could be random. And, it's very important to make sure when
Hmm.
you're presenting experimental results to executives that they understand that there is still, all we're saying is that there is a, certain percentage chance of the null hypothesis, right? Like
Yeah,
we're
sure.
not saying
Hmm.
definitively this had a negative or a positive impact.
Hmm.
It's a very hard thing for some executives to wrap their head around, unfortunately. But it's our job as data scientists to convey that,
Hmm.
right? And there are a few other things that can throw a wrench into measuring the results of these experiments. So one is the novelty effect. This is something we kind
Hmm.
of learned the hard way over a long period of time. So especially when you're testing changes on a website, people get used to the way the website looks today, and any change is going to catch their attention.
Hmm.
So it could be that anything you change, whether it's good or not, is gonna like result in moving the needle one way or the other.
I
Just because
see.
people are like,
Okay.
oh, that's different. I'm gonna like go poke at
Yeah.
that and see what it does. But that's not gonna last forever. Once that novelty
Hmm.
goes away, you can't really measure that effect anymore. So what do you do about
Hmm.
that? Um, you need to have really long experiments to try to like rule out the novelty effect. And we tried doing that for a while. We had what we called continuous web labs that just ran forever.
Hmm.
And we, would reevaluate those over time to see if it was just a novelty effect or not.
Hmm.
As you can imagine, trying to keep these forever web labs from interfering with each other turned out to be basically an intractable problem. So that didn't really
Hmm.
end up to be a solvable problem, I'm afraid. One other thing you can do is just rerun the same experiment like a year later
Yep.
and, see if you get the same results or not. If not, then you can say, well, maybe it was just a novelty effect. So that's
Hmm.
in practice a simpler way to deal with that problem. Also, seasonality is an issue, of course. If you're at Amazon, people behave different around Christmas time than any other time of the year. And if you're running an experiment at Christmas, all bets are off, right? People just behave differently that time. Same thing during the summer, people just act differently. So again, it's a danger of running a short-term experiment because
Hmm.
not only are you up against novelty effects, you might be against seasonal effects that you're not measuring either.
Hmm.
And again, the answer is to rerun the experiment at a
Hmm.
different time if you can.
Yeah, so the web labs was just completely off during Christmas, basically.
Oh yeah. Well, I mean, during Christmas we had code freezes anyway because we were terrified of breaking the site at that point. So,
Hmm.
in practice, that didn't really happen.
Hmm.
The other issue is selection bias, which happens surprisingly frequently. So, you might think that you're randomly assigning people to one treatment or the other, but maybe you aren't, right? And this
Hmm.
actually happened to us a few times. So, for example, if you have a hash function to very quickly assign people into one treatment or another, maybe there's
Hmm.
some bias baked into that hash function that you don't realize. We had one situation where it turned out that lower customer IDs had a higher likelihood to end up in one treatment than people with a higher customer ID because of the hash function we
Hmm.
chose. And it turns out the people with lower customer IDs are longer term customers of Amazon. So they're your
Hmm.
best customers. They behave very differently than everybody else. And that actually messed up our
Okay.
results for a while. So
Hmm.
a way to protect against that is what we call an AA test. So actually run a test of the same thing against the same thing and make sure
Hmm.
that you don't get a result, right?
I
If you
see.
do, then there's
Okay.
something wrong
That's
with
a
how
good.
you're assigning people
Hmm.
to treatments.
Yeah, good thing to know that around this one on selection bias. Thank you.
Yeah, for sure. And you just need to audit those algorithms periodically to make sure
Hmm.
that they really are being assigned randomly. Well, of course, true randomness is impossible, but as best you can.
Yep.
The other issue is data pollution. So crawlers, robots, they tend to pollute your data a lot.
Hmm.
So you got to be careful about that. Even for purchase-based data, we had a problem. We had these institutional buyers that would like buy up
Hmm.
tons of stuff for, a college or a big company, and they tended to have this like really outsized impact on our similarities. So we had to filter those
Hmm.
out once we realized that was going on.
Okay.
So yeah, watch out for outliers, of course. Also
Hmm.
attribution errors, making sure if you're basing the results of your experiment on who bought something that you're attributing purchases to the right thing to begin with. This tends to be more complicated than you think. Those attribution windows might not be quite right.
Hmm.
There might be other changes, in the purchase pipeline that are affecting things that you don't realize. Things can be interfering with you. So also
Hmm.
something to watch out for. And I'm running a little bit long, so I'm going to speed things up a little bit here.
Oh, go.
But yeah, the the way it all ends up is that these algorithms still hold up, folks. It's kind of surprising.
No.
So, I'm still in touch with some of my old colleagues at Amazon who are still there, believe it or not, and they're still using some of these old algorithms there. So you might think that
Hmm.
everything is, AI and large language models and transformers, but this
Hmm.
stuff has stood the test of time. And again, these old school
Hmm.
collaborative filtering methods that can, run on a single server, they can still outperform modern AI approaches. And I see
Hmm.
this in the academic literature too. They use these old algorithms as sort of a benchmark. And
Hmm.
if you read like the papers that are trying to do recommendations using transformers, they often cherry pick their results. So they're like, well, okay, the old algorithm
Okay.
actually beat us most of the time, but we found this one category where we did better.
I
So,
see.
even today, simplicity wins the
Hmm.
day sometimes.
Hmm.
That said, though, there's a lot of similarities between what we were doing back then and how transformers and LLMs work today, right? So we talked
Hmm.
about cosine similarity. That's exactly how vector stores
Exactly. Yeah.
work
Hmm.
in retrieval augmented generation, right? We take those tokens of the words, we make
Hmm.
an embedding vector from that sentence or whatever it is, and
Hmm.
we find the cosine similarity between your prompt and the sentences that we're trying to
Hmm.
use as a grounding truth. And also, you can think of neural networks as a giant sparse matrix operation,
Hmm.
which is exactly what we're doing with collaborative filtering. So mathematically, they're not really that different. It's just a simpler way of
Hmm.
approaching it.
I see.
So yeah, I mean, I preached simplicity back then, and I still do to this day. I have a whole talk on keeping it simple. And also, just a reminder, this is still artificial intelligence. So artificial
Hmm.
intelligence includes machine learning, which includes classical machine learning. So
Hmm.
not all AI means large language models, people, or agentic AI
Hmm.
or whatever. Yeah, so I mean, things did kind of move over time. Like my job was to try to make it better, and we
Hmm.
experimented with a lot of fancier algorithms like HMMs and rules-based systems and trying to find latent vectors. None of them worked. They just turned out to be more complex and more difficult
Hmm.
to maintain, but they didn't really produce better results at the end of the day. So simplicity won the day. But those simple algorithms ended up getting repurposed for a lot of other things on the website. So email targeting, for example, or homepage optimization, ad
Hmm.
targeting. Back before ad targeting really took off. I actually have a patent on something
Hmm.
about related to that. But the other thing is like you don't have to do just people who bought this also bought or people who viewed this also
Yep.
viewed. You can apply that same algorithm to anything you can put in those two holes, like people who searched for ultimately bought or people
Hmm.
who
Yeah.
clicked on this ad, bought this. So you can use the
Hmm.
same technique in a lot of different ways that can be very valuable. And of course, similarities and recommendations aren't the only applications of AI and machine learning at Amazon. It's used heavily in fulfillment operations. How do I get stuff delivered to you in the most optimal way?
Hmm.
That's a huge problem that I had nothing to do with. Supply chain, how do we get stuff in the warehouses to begin with? Fascinating field, which I had nothing to do with.
Yeah.
Search, though, that was actually under our department for a while. And again, the insight there was if you just compute people who search for ultimately bought this,
Hmm.
just mapping keywords to items using the same exact technique, that works
Oh, okay.
surprisingly well,
Hmm.
which is surprisingly simple. Demand forecasting, of course, people trying to figure out who's going to buy what when, organizing the categories that new items get put into, that was also a
Hmm.
big problem. And just a side note there, data labeling was a very early problem at Amazon as well. And you
Hmm.
might remember Mechanical Turk, where they kind of sold this as a service to hire outside data labelers to actually label your data for you.
Hmm.
That turned into something a little bit ugly, I'm afraid, but they were a pioneer in that space as well. And we also tried to expose personalization as an AWS service. They actually have one these days, but
Oh, okay.
at the time, this was like 10 years before the one that they actually ended up releasing. I
Oh,
led
okay.
a project to build an AWS service for personalization that would give, product recommendations to any site that wanted them. And like right before we were about to launch that, we had a review with Jeff Bezos, and he
Okay.
decided to kill the project at that point
Oh, okay.
because he's like, no, this is Amazon's secret sauce. You can't give this away to other people. I don't care how much you're going to make from it. So
Wow.
I went back
That's a
with my tail
bold
between my legs
decision.
and told my team they had to go do something else. So, um, but apparently 10 years later, he changed his mind, or maybe he just checked out by that time.
Yeah,
Yeah.
that was my question. Like, what changed his mind 10 years later?
Probably Lauren would be my guess.
Hmm.
He met his new wife around that time.
I see.
But I won't go into that in
Hmm.
too much detail. But he did kind of check out around that time. And,
Hmm.
just just to reiterate, the CEO of Amazon today is Andy Jassy. It's not Jeff Bezos. So a
Mm-hmm.
lot of people, blame Jeff Bezos for everything Amazon is doing these days, but he really doesn't have much to do with it at all anymore.
Mm-hmm. I see.
Also, I moved to IMDb after that and ran IMDb for a while, and obviously movie recommendations at IMDb uses these techniques
Mm-hmm.
as well. Fraud detection, of course. And back then, we didn't use GPUs except for playing video games. So yeah, no
Well.
GPUs required. Imagine how much faster it would be today. Now, they did release another service after I left called Amazon Destiny. They kind of open sourced kind of what they said was what they were using for personalized recommendations within Amazon.
Mm-hmm.
I'm not entirely sure I take them at their word at that, but basically they were just exposing a way of setting up a deep neural network. So this is what one of their config files
Oh,
looks
okay.
like. And it looks exactly like, setting up something in Keras or something for, stacking
Mm-hmm.
up layers of a deep neural network. So, you could think of you could frame the same problem as saying this vector is going to be the input to the bottom of a neural network. If we have
Mm-hmm.
come up with a way of dealing with the sparseness of that array, and out the other side comes your recommendation. So, perfectly valid
Mm-hmm.
way to do it. A lot more complicated, but that also works too. So they did actually release a system around that, which implies that they were at least experimenting with that internally after I left.
Yeah. Mm-hmm.
Anyway, how it ended up. So, unfortunately, today, real similarities and recommendations are hard to find on Amazon because they've largely been replaced by sponsored placements. And again, I think Jeff would be rolling in his grave over this maybe because, Amazon always talks about being very customer centric, but, when you're putting
Mm-hmm.
sponsored placements in front of people, that's really, well, shareholders centric, right? So, if you go and look at a product detail page right now, today, you're going to see a widget that looks like this that says products related to this item. Sounds like it's similarities, but then there's this little like sponsored link next to it that says, actually, people just paid to put this on the page. So it might not be the best recommendations
Oh,
for you
okay.
after all. So watch for that sponsored tag, people. It's a giveaway.
Oh,
The
I
real
didn't know
value,
that actually.
yeah.
That's a great news.
Yeah, I mean, the real value for AI and ML, of course, is in Amazon Web Services. They're making a killing off
Mm-hmm.
of SageMaker and Bedrock and all the certification exams surrounding that and kind of
Mm-hmm.
selling these capabilities at scale to other companies. So they're kind of
Mm-hmm.
the people selling the shovels to the gold miners, right?
Mm-hmm. Yeah.
Certainly, they still use this stuff internally deeply, but they don't talk about that at all. They're very secretive about what they do. So I'll wrap up on what everyone wants to know. What was Jeff really like? Yeah, the cool thing about working at Amazon back then is that you ran into everybody all the time. So it was
Mm-hmm.
much more contact. I had like regular quarterly meetings with him, and just ran into
Yeah.
him in the hallway, stuff like that.
Mm-hmm.
Yeah, I like the guy. Like he's definitely the smartest guy I ever met. He's very focused, of
Oh.
course, very has high expectations
Mm-hmm.
of others, which as you would expect. I would characterize him as strict but fair, kind of like Professor McGonagall
Mm-hmm.
in
Okay.
Harry Potter. There are like some legends about how Amazon operated internally during the early days. Some of them are true.
Mm-hmm.
One that is true is the six pager. So,
6 page. Yeah, I've heard of
yeah,
it.
yeah. Any meeting that you had with executives at Amazon, you had to come prepared with a very meticulously thought out six-page
Mm-hmm.
document of what you wanted to talk about. And at the beginning of
Oh.
the meeting, everyone would get a
Mm-hmm.
copy of that. You'd sit there and watch them read for about 20 minutes, and then they start grilling you at the
Oh.
end of that meeting.
Was
And
that really effective though? What do you think?
I mean, in the context of busy executives who don't have time to read stuff ahead of time, then yeah, I think it was super effective
Mm-hmm.
because first of all, it's going to be fresh in their mind because they just read it, right?
Yeah,
And second
sure.
of all, they're forced to read it. And the act of
Mm-hmm.
making that document forces you to be super crisp about what you want them to think about and what
Yeah, makes
answers you
sense.
want
Mm-hmm.
answered, right? So,
Mm-hmm.
um, Jeff was always a form of long form reading. He wanted people to
Mm-hmm.
like really go deep into a topic and internalize that. And a six-page document was a way to do that.
Mm-hmm.
As an aside, that's what actually inspired the creation of the Amazon Kindle. He wanted to keep long form reading
Oh, yeah.
alive.
Mm-hmm.
That was the ultimate goal
Oh,
there.
great
Um,
motivation there.
yeah. The other myth is two pizza teams. These were a thing for a while. And if you're not
Mm-hmm.
familiar with the concept, the idea is
Yeah.
that no team should have more people on it than you can feed with two pizzas. And they should be
Oh,
completely
okay.
autonomous and self-contained. And that
Mm-hmm.
way people can move quickly. They have one thing that they're focused on that they're trying to optimize, and they have no external dependencies holding them back. Sounds great on
Mm-hmm.
paper. Um, and we tried that for a while. So I ran a two pizza team for a while. We had to come up with a fitness function for personalization that's basically measuring,
Mm-hmm.
how good are we at serendipitous discovery at the end of the day. And for
Mm-hmm.
us, we made it work. But for most teams, you just can't eliminate those third-party dependencies or those dependencies outside of the
Hmm.
team. And that ended up killing the idea pretty quickly. I think they
Hmm.
tried it for like a year or two. And after that, they
Hmm.
kind of threw it away. But there's still management
I see.
consultants out there, saying
Mhm.
Amazon uses two pizza teams and you should too. Like, no, they stopped using two pizza teams like 15
Hmm.
years ago. So, it's still a good
Okay,
idea, maybe in
good to
some
note.
situations, but
Hmm.
it has scaling problems, is what it
Hmm.
comes down to.
I see.
Also, he's a science fiction fan. So the first time I saw Jeff, he was dressed up as Captain Picard from Star Trek: The Next Generation. It
Really?
was it was Halloween, so I guess it's okay. He was
Okay.
like trick or
Hmm.
treating with his wife and kids.
Hmm.
But if you talk to him, like when he's off the clock, he did talk a lot about space. And today
Hmm.
he is more involved with Blue Origin, his space
Hmm.
company, than Amazon, I would say. In fact, they're about to launch the second test flight of New Glenn later
Hmm.
this month, so
Yeah.
watch for that. But yeah, I mean, kind of like, Elon Musk is like trying to like generate money for SpaceX through Tesla
Hmm.
and everything else. His original idea was to just do Amazon to fund his space ambitions, right? Uh,
Hmm.
but for him, the focus was a little bit different. He's not trying to go to Mars.
Hmm.
There's another like futurist, Gerard O'Neill, I think was his name, that was more influential to him. So he wanted to just
Okay.
he's more about moving manufacturing and, dirty industry into
Uh-huh.
space where it
Okay.
can't do any harm. So he's more
Hmm.
about giant space stations than,
Hmm.
moving humanity off planet. But yeah, it was a little bit surprising talking to him about that because that's really where his passion lied. And I think it still does.
Mm. Interesting to know.
Um, Another cool thing is that he was always careful to allow others to speak before
Hmm.
him. So he knew that in a meeting, he carried a lot of weight, and anything that he said would
Hmm.
just be latched onto as gospel, right? Because he's the
Mm.
owner.
I see. Yeah.
Um, so a good little management tip there maybe is if you're in that kind of a situation, make sure you talk last,
Hmm.
ingest other people's ideas first, and then let them know what you think about what was
Hmm.
being said. Otherwise, you're just going to influence the room more than you want to, and you won't get any ideas other than your own.
Yeah, makes sense.
Yeah. All right, so yeah, I think we're doing good on time here. If you want to stay in touch with me, you can check out what I'm up to at sundog-education.com. Yeah, what I do these days is teach AI and machine learning and other stuff. So you can see a list of my courses there if you're so inclined, or follow me on LinkedIn. I'm just under F Kane there, and I'm pretty active there, and always happy to connect with people there as well. And with
Okay.
that, if you have any additional
Mhm.
questions, I can take them. If not, we can call it good.
Yeah,
I'll stop
that
sharing.
sounds great, and thank you very much for the presentation. Um, I encourage everyone to ask any questions. Feel free, no pressure on that. But maybe I can kick off with the first Q&A question. And since we're on the topic on the learning parts of the data science, what I was really interested about basically what are the topics or subjects that you would advise others to start with in order to be more if maybe they have already started in data science or they are newbies, like what would be your suggestion how to start it with what topics, and also like since we currently have a big Gen AI hype, what would be your suggestions like how to avoid going too much into that details and actually starting with the fundamentals of everything?
Well, I think you just answered your own question. Like, start with the fundamentals.
Oh yeah.
Like the value is going to be in people that actually understand these algorithms and aren't just
Hmm.
regurgitating what Chat GPT or Claude gave them, right?
Hmm.
So if you're really new to the field, start off with basic statistics, start off with actual, classical machine learning techniques. And it's still true to this day that if you just have like a simple classification problem, you're going to be hard pressed to beat XGBoost or something like that, which is
Hmm.
super simple, right?
Yeah,
Like I can run
that's
that on
true.
my PC under my desk right now. And it's
Hmm.
probably going to outperform what you're doing on your, giant cloud-based neural network and for a lot
Yeah,
less money
exactly.
too. So
Hmm.
and I think that's going to be an increasingly valuable skill to have because
Hmm.
people kind of have this default position of going straight to a large language model or a large transformer model to solve
Hmm.
problems these days. And you have to remember that right now the cost of that is artificially low.
Hmm.
OpenAI is forecast to lose $190 billion in the next 2 years. And
Oh well.
someday the bubble's going to pop and they're going to have to pass those costs on to the consumers and it's going to get more
Hmm.
expensive. And when that happens, people who know how to save money are going to be valuable again, right? So
Hmm.
if you know about these simpler classical machine learning techniques, that can do
Mm-hmm.
the job just as well, sometimes even better, but at a much lower
Mm-hmm.
cost and at much greater simplicity,
Mm-hmm.
you're going to be the hero of the day, right?
Yeah, makes
Um,
sense. A
One thing I
great
would say though is,
suggestion there.
focusing on actual coding probably doesn't matter as much anymore. Totally
Mm-hmm.
fine if you want to use, an LLM to write your Python code
Yep.
to help
Mm-hmm.
you along on that. I don't judge if you do that. I'm doing it myself now too. It's
Yeah.
probably going to do a better job than you will and a
Mm-hmm.
lot faster.
Mm-hmm.
So by all means, leverage LLMs to accelerate your coding when you're writing
Mm-hmm.
your notebooks. But don't lose sight of the classical algorithms out there because I think
Mm-hmm.
they're going to have a resurgence at some point.
Mm-hmm. Yeah. Sounds great. And thank you for answering the question. I think there's one question in the chat. Will there be more courses like this? Um, I think it is regarding the courses that you currently have, and yeah, there are tons of courses that you can check out on Frank's website. So um, yeah, check it out, I guess.
Yeah, and I do see a question just came in on
Mm-hmm.
deploying Python to production. So it depends, right?
Mm-hmm.
Um, if you're using Python as a simple like orchestrator, basically to kick off more efficient systems, cool. I don't care, right?
Mm-hmm. Yeah.
So if I'm using Python to like kick off, a big Spark cluster and kind of control what it's doing, the heavy lifting is being done by Spark under the hood, and that's fine.
Mm-hmm. Yeah.
It just comes down to like optimization best
Mm-hmm.
practices. So
Sure.
if
Mm-hmm.
Python is good for kind of like orchestrating what your pipeline's going to do, that's not where you're really spending your time. But when you're actually crunching
Mm-hmm.
that data at scale, that's what matters. And if you're using something like Spark to do that, it's going to be using Scala under the hood, which is actually pretty darn fast
Yeah.
because that's built on top of Java
Mm-hmm.
bytecodes, which are almost as fast as C. Um,
Yeah. I agree.
so yeah, I wouldn't make a blanket statement. Don't use Python in production, but don't
Mm-hmm.
use Python for really tight loops that run over billions of rows of data.
Yep. Good advice.
Yeah, I see a lot of stuff on LinkedIn like Python is dead. No, it's not dead. It's not going anywhere.
Yeah.
That's just silliness.
Mm-hmm. I mean, it definitely has its own benefits. I mean, we all know that it's very like slow in terms of the execution, but still it has lots of libraries that we can use that are based on different languages that actually make it much more optimized than maybe other solutions. I'm not going to mention the ones, but yeah. Um,
Yeah.
so yeah.
Yeah, Pandas is awesome. Next, scikit-learn is awesome. NumPy is awesome,
Hmm.
but I'm not sure I'd use
Yep.
Pandas for a big data set in production.
Yeah.
In fact, it would just fall apart because it's all in memory. So wouldn't work
Mhm.
anyway.
Yep. All right. Do we have any other questions? I can not see in the chat, but
Oh,
maybe.
there's one.
Mhm.
Rustam has one. So if you use cosine similarity for the recommendation engine, how did you make a model to recommend something completely new for users? Um, Yeah, so that's how item-based collaborative filtering works. Basically, we're looking at the collective activity of everybody else to recommend stuff that you might not have known about. So that really, there's two dimensions to your question there. Like one is how does that work at a low level? So basically, I'm taking a look at all the stuff that you liked, all the stuff that you purchased, and then I'm looking at all the other stuff that people bought who bought that stuff. So odds are somebody who bought that thing bought something you didn't know about, and that's how that data
Mhm.
kind of leaks into your recommendations. The other thing is to try to like encourage that to happen, right? And that's where filtering and ranking comes into play. So
Mhm.
I can explicitly say, maybe there's a level of similarity where it's actually too similar and that's too obvious of a recommendation.
Mhm.
And I don't want to show that. I want to show the more interesting ones that are kind of in this sweet spot of maybe like 70 or 80% or something like that.
Yeah, I see.
So, you do have these knobs and dials you can twist to say, how novel are those recommendations? How serendipitous are they likely to be? But again, it just comes down to the scale of the data that we're dealing with, because there are so
Mhm.
many other people on Amazon, chances are there's somebody who knew about something you didn't know about. And we can like connect them to you and kind of like let you share your recommendations with each other through these algorithms.
Mhm. Got it. Thank you. Great. All right. Any other questions?
I think we're good.
Yep, I think we're good. And yeah, thank you very much, Frank, for today's meetup. And I'm very glad that I've had my very first meetup with you. And I think there's going to be a lot of takeaways from this meetup. And yeah, thanks. And thanks everyone who attended as well.
All right. Thanks for having me. Take care.